So the thing I'm curious about looking into today is whether you can use your phone as a metal detector. Now, this is a pretty ridiculous claim to make, so I want you to just take a moment and think about how you might use your phone as a metal detector. Okay, so my idea, I feel like there's a few levels of theory that we need to look into before we fully explain what my idea is. So to start off with, what we found previously is that you can use magnetometer on your cell phone and you can combine that with AR, and in that way you can get a free floating vector field of what the magnetic field is. And so that's a really important part of how we're going to use our cell phone as a metal detector. So I want you to just, knowing that fact now that we can get these floating vector fields, how would you find metal based on that? Okay, so the next part I wanted to talk about is just a basic reintroduction of some traits of magnets that sometimes people forget. So if an object is in a magnetic field will be induced within that object. And in particular, this is very strong in metals and in particular iron. So if you notice, sometimes if a piece of metal gets close to a magnet, it will magnetize, and it doesn't actually have to touch the magnet. So it can be nearby the magnet and it will become magnetized by being in that magnetic field. And so just taking a moment now and thinking about what giant magnetic field is around everywhere. Okay, so I think we have all the parts now. So basically the idea is that the Earth's magnetic field will induce a magnetic field in any large metal object, and by measuring the gradient in the magnetic field, so by subtracting out the Earth's magnetic field, we should be able to see magnetic fields coming from those objects. And furthermore, if the objects are very symmetrical, there should be a very simple magnetic field. It should be a magnetic dipole. It's probably a little bit more accurate to say that it would be a multipole and that we could do some sort of expansion with it. But for the most part, a dipole is probably good enough. So what we're going to do is we will measure the magnetic field near a metal object, and then we will try and match a magnetic dipole and fit it to that magnetic field. And so this is a lot. Some of these steps are very complicated, so we'll just try them out and see how that works out. So, as it is, this is not actually a particularly useful thing to know because the metal that you would be detecting is both very large and also has to be very symmetrical. So, if it is an odd object, it will have the dipoles will all kind of be combined together and you'll end up with a rather odd magnetic field. So, yeah, it's basically limited to large symmetrical objects, which is not particularly useful, but it's an interesting start. And the other thing that is kind of interesting to think about, the Earth's magnetic field is not necessarily the strongest magnetic field because it's very spread out. And so if you actually had a more localized field, then perhaps you could create larger induced magnetic fields, and that would allow you to see objects more quickly. So yeah, there's a bunch of interesting ways of sensing magnetic fields, but I just think it's a really interesting start to a project. This is not going to be a replacement for metal detectors at an airport or anything, but if you did have a large magnetic field that you could induce, then you could end up doing some of that similar work. So it is an interesting start. So if you apply this to a bunch of different magnetic objects, you'll find that the dipole doesn't converge consistently to the point that we would, to the location of the metal. So overall, we get about 2 out of 8 in terms of the success rate. So this needs a lot of work, but even when it doesn't hit it exactly, you can kind of tell if we had a better modeling system. There is a signal, it's just finding the signal is a little bit more challenging than you might expect. So there's more work to be done here. Okay, so we're going to be starting from our previous magnetic field experiment where we just found the magnetometer and managed to put it into AR. And so that'll help us start off much quicker. And so we need to start by initializing some of the event listeners, and those are basically just going to flip flags in our code. And then we're going to initialize some new values. So this has to do with the magnetic moments that we're going to be predicting and the location of that magnetic moment. And then with our flags, we're going to change it so that before we just recorded a set amount of backgrounds and then did the average of that. Now we're going to incrementally change our background each time we add a new value to our background measurement, and we will color our background in a bluish color. Our normal measurements will be in a yellowish color, and then we will add our recorded values in a reddish color, and we will add those to the recorded list. So the recorded list is the list that we are going to be using to predict where the location of the induced dipole is. So on each frame, these things happen. So each time the frame is rendered, we will do one step in the gradient descent. And so to start off with, we need an initial prediction. And so our initial prediction is just going to be the average of our recorded values. So this is something that to just think about whether we might be overfitting at this point, because we are already starting very near to where our prediction is. So this system might not actually be the best at predicting distant objects. So now we're going to call the gradient function. We haven't actually built this function yet, but we are going to put in a position and a moment, and we're going to expect back out a position and moment. And then we are going to draw a new set of lines. These are going to be a dipole field that we are going to write later on. So this is going to be a set of lines. Okay, so now we are going to create something to parameterize the magnetic field. So we are going to have to calculate a lot of magnetic fields. So we're going to build a function that returns a function. So this is sort of like a factory, and with that function, we are going to be inputting the expected moment and the expected magnet. So these are the predictions that we are making. And then we have to have our measurements. So these are what we measured with our magnetometer. These are going to be the red arrows. So then we have to calculate the radius. So from where our position is subtracted from where our expected moment is. So this is kind of the theoretical radius that we have. So now what we're basically doing is we are calculating a magnetic field from our theory, and we're subtracting it by the measurement that we have done. And so in principle, if this is perfectly optimized, it should end up being 0. So this can be thought of as a reward function. So we want to eventually get this value down to 0. And then we'll also just write a magnetic field function as well so that we can do our graphing. Okay, so now we're going to do our gradient descent. So we have to initialize some axes vectors and the different learning rates, and the diff h is basically how much we're doing our differential by. So here is our numerical derivative, and our numerical derivative, basically what you do is you change the value by a little bit, and then you subtract out the original value, and then you divide it by a really small number. So diff h just needs to be a really, really small number. This looks very intimidating, but if you kind of work through it, it actually is just the differential on the magnetic field. So this will be the gradient that we are calculating for each of the positions. So X, Y, and Z. So now we're going to go through our measurements. These are the measurements that we have taken, and we are going to create the differential for each one, and then we're just going to add those together. So we're just summing up the different for each value. Each recording is basically giving us a differential on it, and we're just summing those together. And then the gradient descent part, we take our value and we multiply it by the learning rate. And so one of the things that comes up with magnetic fields is they have so many, there are going to be a lot of infinities in here and a lot of poles, so like infinite poles. So basically I found that it works a lot better if we just do a sign of the value. So we're just calculating out what the gradient sign should be, so whether it's positive or negative, and then just moving it by the resolution that we have. So our resolution in this particular experiment is about 1 centimeter. So if we just move it by the sign distance in 1 centimeter, that's going to converge fast enough. And once it gets to its conversion point, it'll just kind of oscillate around that area. So it'll just kind of flick around the centimeter distance. And so when I tried doing this without the signs, it just kind of flew off into infinity. And like that happened I've had some really difficult times getting this to work. So I think that just using the sign multiplied by the resolution is probably the easiest way of doing this. So yeah, that's what I'm going to stick with for now. Originally, I was trying to calculate out the magnetic moment as well. And so you could do a gradient descent for the moment as well. But I found that just cutting it parallel to the background, so basically just copying it over and over again, it was too difficult to actually do all of this at once. So maybe in the future, I'll look more into trying to do a gradient descent for the magnetic moment in the same period of time. But okay, so now to graphing the lines. So we just have to have our position and our moment, and then we are calculating out the direction and position, creating a set of starting positions in spherical coordinates, and then we're converting those back to Cartesian coordinates, and then we're just applying and adding the position of our expected dipole. And then what we do is we just take those starting positions and we just slightly move them forwards in the magnetic field, and we just keep doing that, and then that draws out the magnetic field line. And then the rest of this is very similar, simple 3GS plotting. The one thing that we also wanted to add is something that removes previous plots so that we can add more and more plots without running into issues. So that's what that is. It's just cleaning up the old set. We basically just plot out the lines. This is kind of the formula that you use for plotting out lines. You have to kind of set some arrays iteratively. After I finished this, I realized that I should probably be using a web worker. So I modified some of this to just add it into a web worker. So that is on GitHub if you need it. I'm kind of curious about whether neural networks would be useful at all for this, but I kind of need to create a special reward function. So that's probably a future project. If you had any difficulties with this, the previous video with magnetic fields is here, and have a good day.